Hi, everyone. I'm Long Huang from Louisiana State University. Today, I want to introduce our work, notification privacy protection by unobtrusive gripping hand verification using media sound. The authors are me and my advisor, Dr. Huang. Smartphone notification can leak users' private information in a locked screen. For example, the email and message content, contact information, social network, account transactions, and personal reminders. When the smartphone is placed on the table or shared with others, this sensitive content could be leaked. And to prevent such privacy leakages, many authentication methods have been deployed to protect the access to the device, such as pins, lock patterns, fingerprints, and face recognition. While these methods all require human efforts and could not cope with notifications showing automatically. And to address the notification privacy, mobile operating systems allows turning off some apps notifications through offline configurations. And Android supports setting up multiple accounts such that the smartphone can be switched to ghost mode when needed. And iOS introduces the guided access feature, which allows the user to restrict phone usage to a single app and also disable all the notifications before handing the device to others. However, these methods all impose the responsibility on the users to decide when to display or hide the notifications, which do not work for the device sharing and notification scenarios. And instead, this work aims to develop an unobtrusive user authentication method, which verifies the user before displaying the content of a notification, which could balance the privacy and the usability. And we start our work by conducting an online survey to study the user's concerns about the smartphone notifications. And in a 9-month period, we received 111 respondents. When being asked, do you have privacy concerns for smartphone notifications? 74% of the participants answered yes, 10% are not sure, and only 16% answered no. And their major reasons are, I never shared my smartphone with others, or I can handle the privacy issues by myself. And we also noticed that 75% of the iPhone users and 65% of Android users have never heard of their smartphone security features to protect the notification privacy. And in comparison, 72% of the participants want a low-effort solution that can handle the notifications smartly according to different scenarios. And as the notification always comes with a piece of media sound, we decide to verify the user by distinguishing how they grip the smartphone using the notification tones. And specifically, when notification comes, the sound played by the smartphone speaker traveling along the smartphone surface will interact with the user's gripping hand before reaching the smartphone microphone. And since people's hand geometrics and gripping strengths are unique, they exert different effects on reflecting and absorbing the original tone signal. The resulting signal would then carry the user's hand grip biometric. To show the feasibility, we play a long beep signal consisting of 5 single-frequency sinusoid waves using the smartphone, during which the smartphone is gripped by 2 users' hands. And we then derive the acoustic response captured by the microphone, as well as the vibration response captured by the accelerometer, to capture the user's hand grip biometric. As shown by the left figure, the smartphone sound at different frequency is uniquely affected by the user's gripping hand. And the signal exhibits distinctive patterns among the 2 users' gripping hand. And the frequency selectivity indicates that we can utilize the rich frequencies of the notification sound to capture the user's hand grip biometric. And also, similar as shown by the right figure, the vibration response also exhibits distinctive patterns among the 2 users' gripping hand. And due to the low sampling rate of the accelerometer, the data collected by the accelerometer has a nonlinear relationship with the real surface vibrations. And we now introduce the flow of our system. When notification comes, the acoustic response and the vibration response are captured by the smartphone's microphone and accelerometer, respectively. Data pre-processing is first performed to denoise, synchronize, and segment the 2 modalities data. And the core of our system consists of 2 components. One is the two-domain user verification. The other one is the cross-domain validation. The two-domain user verification derives a microphone and accelerometer spectrogram to capture the user's hand grip biometric and feed them into a SIM-based model for user authentication. And the cross-domain validation examining the unique physical relationships among the two modalities data to determine the authentication validity. Then based on the SIM scores and the SNR differences coming from the cross-domain validation, the cluster-based method determine whether an authentication request is from the user, the non-user, or attacking sounds. And the two modalities data suffer from different type of noises. For the acoustic response, we apply specific bandpass filter for each tone signal to focus on its frequency range, which removes the low frequency mechanical noises as well as the high frequency noises. While for the vibration response, we simply apply a high pass filter with a 40 Hz cutoff frequency to remove the noises caused by the hand vibrations, which can be expressed by the bottom figure. And to find the starting point of the acoustic response, we use the original tone signal as the reference and iteratively shift the recorded signal and computes its cross correlation with the reference. And the maximum cross correlation indicates the delay for synchronizing these two signals. While for the vibration response, we downsample the original tone signal and use it as a reference, which would then have the same sampling rate as the accelerometer. We then derive spectrogram to capture the user's hand grip biometric in time frequency images. And the spectrogram of the data sequence can be computed based on the short time Fourier transform, which can be expressed by this equation. And each pixel of the spectrogram can be obtained using the second equation. And as shown by these figures, the acoustic response and the vibration response under the same tone signals are both distinctive among two users' gripping hand, meaning that the hand grip biometrics can be leveraged for identifying the users. And we use CN to learn the hand grip biometrics embedded in the spectrogram we derived. And we develop a CN model with 5 convolution layers and, where the spectrograms of the acoustic and vibration responses are taken as the input. And since our system supports multiple enrolled users, the CN scores, the probabilities are output for all the enrolled users class as well as the non-user class. And the trained model has around 58,000 parameters at a size less than 0.3 megabytes, making it suitable to be deployed on most mobile devices. And to prevent the attacking sound launched by the external speaker, we propose to examine the unique geometric relationships among the built-in speaker, the microphones, and the accelerometer. And specifically, we derive the SNRs and compute the differences which are of the data recorded by the microphones and the accelerometer. And since the external speaker is located outside of the target device, it is hard to forge the physical relationships between the built-in speaker, the microphones, and the accelerometer, which are on the same motherboard enclosed by the smartphone case. We then conduct the fundamental study to examine the cross-domain SNR relationships between the between the accelerometer and the microphones. And we consider 3 types of external sounds, where the external speaker can be placed on or not on the same surface of the smartphone, or the smartphone is directly placed on the speaker. And the intuition is that the vibration of the external speaker can help to forge the vibration response of the smartphone. These 2 figures shows the SNR relationships between the accelerometer and the microphones. We can observe that the yellow curve, which is the SNR curve of the built-in speaker, is isolated from that of the 3 external sounds, which means that it is hard to forge the SNR relationship exerted by the built-in speaker. And we also noticed that the external sound not coming from the same surface as the smartphone could hardly generate the vibration response at the smartphone, meaning that the acoustic noises can hardly influence the vibration response, which we will talk later. Then the cluster-based method integrates the CN scores and the SNR differences to determine whether authentication request is from the user or the non-user or other resources. And the user's cluster is obtained through the enrollment, which is differentiated from the clusters of the non-users and replay attacks. Although we observed that the replay attacks shows relatively high microphone saying scores, but the accelerometer saying scores are low. And in comparison, we observed the non-user class shows similar SNR differences as the user class, but both the microphone and accelerometer saying scores are low. The results indicate that it is hard to forge the two domain features simultaneously. We then evaluate our system on 4 different device models, which are all embedded with 2 microphones and 1 accelerometer. And the experimental platform is developed on Android 9, which uses 1 thread to play the sound and use another thread to record the vibration and acoustic responses. And the tones being played includes 6 types of short message tones as well as 3 ringtones. We recruit 30 participants and collect the data in 2 sessions, with the first session being used for training and the second session used for testing. And we first present the overall performance of our system. This figure shows our system achieve a high performance of identifying the users using all line tones, achieving an accuracy over 90.4%. And with iPhone message, Nokia Ring achieving accuracies around 95%. The results indicate that our system generally works for different notification tones. And since different device models have different configurations of accelerometer microphones, different sizes, different shapes, we thus evaluate our system using 4 different device models. The figure on the left shows the user verification performance of our system on 4 different device models, achieving accuracies between 92% and 95%, meaning that our system generally works for different device models. And in regarding to the multiple enrolled users case, we found our system performance slightly decreases when the enrolled user increase. And to study the impact of the acoustic noise, we evaluate our system under different types of daily noises whose sound pressure level ranges from 40 dB to 80 dB. And these 2 figures shows our system performance slightly decreases. It does decrease as the noise level increases. And specifically, as shown by the right figure, the performance of microphone 1 decreased from 92% to 86% when the noise level is increased to 70 dB. But the performance of the accelerometer sees little impact, which is the yellow bar. The reason is that the accelerometer is relatively isolated from the external sound, which we have discussed before. And by integrating the 2 modalities data, our system can still achieve 91% accuracy of identifying the user, even under a 70 dB noise. And we further investigate the notification scenarios when using the music tones could disturb people, such as in the museums or during the conference. And we also noticed that in order to still be notified, the users always set the vibration alert as a notification signals. By considering the vibration alert as a special tone, we extend our method to work in the silent mode. And we then derive the acoustic and vibration response of the vibration alert for user authentication. And we found that although the accelerometer mainly captures the phone's vibration at a frequency around 157 Hertz, the smartphone microphone can capture the vibration sounds of up to 20 Hertz, which includes the harmonics as well as the smartphone surface vibrations. The figure on the left shows the user verification performance of our system using the vibration alerts on 4 different device models, achieving accuracies all over 95%. And here comes the conclusion. This work provides an unobtrusive solution to protect the user's notification privacy in both silent and non-silent smartphone modes. We showed that the smartphone media sound can be used for sensing and verifying the user's gripping hand. And we then derive spectrograms to describe the user's hand grip biometrics in acoustic and vibration domain, and develop the same-based algorithm for user authentication. We also derive the unique cross-domain physical relationships among the smartphone's built-in speaker, microphones, and accelerometer to verify the authentication validity. Extensive experiments show that our system verifies the users accurately and effectively prevent external replay sound. Thanks for listening. Please be free to ask questions.